This is Experiment 17, Set Your Tone, of Make Electronic 2nd edition by Charles Platt. We've covered two separate modes of the 555 timer in Experiment 16. The first was a monostable mode, which we saw could be used to create pulse sequences at fixed delays. And then we saw in 16b the bistable latch. Today we're going to look at the third and final 555 common operating mode, which is called astable. And what that means literally is not stably in simply one state, but actually switching back and forth between two states. And because the timing of that switching is very precisely controlled by the components we attach to the 555 timer, we get an oscillator with a very precise frequency. So bring up the internals section under the 555 timer, and here you will see the external components to the IC outside the box, particularly resistor 1, resistor 2, and capacitor 1. And then there's a control, not connected for the moment. To resemble the circuit we're going to build, we'll actually change the supply voltage to 9 volts, the rail voltage going into R1 to 9 volts, and a couple of 10K capacitors, one to the discharge pin, one to the trigger pin, and the threshold is connected to the same wire as trigger in this case. C1 is connected from threshold to ground, and of course the circuit's power supply, or the IC's power supply, needs a ground as well. And the output we're viewing on the oscilloscope at the bottom of the page, along with some of the intermediate waveforms. Let's take a little look at the circuit operating, and we notice how it is that it seems to oscillate or achieve the astable mode. The capacitor both is charging and discharging. When the threshold and trigger reach points where they would flip the flip-flop part of the circuit, the flip-flop is internally connected to that discharge pin via transistor. So there's a transistor base, comes from the flip-flop. It's the opposite of what goes to the output. And so it starts to drain the RC network circuit once the trigger and threshold pins are exceeded. And that draining of the circuit is what makes the current move the other way in the RC network, then stops the discharge from flowing eventually, and the whole cycle repeats. The R1, R2, and C1 values set the oscillation frequency, in particular how long the signal is on versus off. Now, currently, it's reading about 150 hertz, so that's sort of an audio frequency. As we change the resistor values, you'll find that the duty cycle changes. And duty cycle is, say, how long in a particular cycle the signal is high as opposed to low. So right now we have a higher duty cycle by increasing R1 and leaving R2 and C1 the same. However, the frequency has also changed. So the frequency depends on all three of these. And if we want to get, say, a different frequency but still have a equal duty cycle, half on and half off, we need to make the second resistor the same value as the first one. And now you see we have a much longer frequency, but with approximately an equal duty cycle. Of course, you can put potentiometers in and use those to change the values of R1 and R2 to get variable frequencies. You would have to change both of them at the same time, however, to keep the duty cycle the same. Changing the capacitor is a straightforward way to change the frequency. It's pretty simple. As we increase the capacitance, it will take longer to charge because we have a bigger balloon to hold up charge. You have to actually speed up the simulation, or you'll be waiting all day to see it turn on and off. And this is how we can move our 555 timer in astable mode down to slow frequencies, say for blinking an LED. And that's what I'm going to show you next, but I'll be using the disintegrated circuit from Evil Mad Scientist. You'll be building it with your integrated circuit at home. So in a low frequency example, I've adjusted R1, R2, and C1. So I've got power hooked up to my IC, to the rails, 9-volt battery. I have coming from R1 on the yellow cable going to the discharge, so that will drain the RC circuit when it's time to flip. I've got 2 wires coming off R2, one to the threshold and then the second one to the trigger, because those are going to be firing at the same time. And then the output is on a white cable, and I have it going just through an LED and resistor. Now this is different than what is shown in figure 422 in the textbook. They don't do a blinking LED, but I would like you to do one first in the circuit. You have to choose R1, R2, and C1 appropriately. I've purposely made sure you can't just cheat by looking at my video. Now when we do go up to higher frequencies, it's different choice of resistors and capacitors. You can use the suggestions for R1, R2, and C1 in the textbook. You need to use a coupling capacitor out to a speaker. I'm using an external speaker to make sure you can hear my example. Again, I'm actually using still my disintegrated circuit. Same configurations with power. And instead of that complex formula for determining the frequency, you can instead use table 425 in the textbook to select your resistors and your capacitors. And of course, you'll be putting everything on the same breadboard rather than running a bunch of wires around. Again, you can stick potentiometers in for these resistors and change the duty cycle and the frequency and listen to that. And that makes a nice controllable signal. But what I'd like to talk about next is actually a way that we can make some more modular electronics by, instead of building in knobs that we have to fiddle with to change frequency, maybe control one electronic circuit with another. And for that, we're going to introduce the control pin. That's the one pin we really haven't talked about much yet. To see what that does, we're going to go and stick in the simulation here separate external voltage. It's not going to be 9 volts, some other intermediate voltage between, say, 0 and 9, and we'll take that and stick it onto the control voltage. But first, since we're in the audio frequency range, let's bring in the audio output. And I have to hunt around to find a place in the Lush project simulation to place the audio output. But once I stick it to a node, I should see that play audio button pop up under the circuit. And once the data requires for a little while, I can actually listen to my tone. Then free to go around, tweak components, and see how they change the frequencies. But back to the control voltage. Let's grab a external wire or external voltage source and hook it up, and notice how the control voltage goes directly into those comparators, which in turn trigger the flip-flops. So by raising or lowering that control voltage, we will change when it is with respect to the RC network that the flip-flop fires. Furthermore, the control actually also goes over to in between those two 5K resistors. So we have quite a wide range of external frequency control by adding a external voltage. In other words, controlling one circuit with another. So to demonstrate that, I'll grab one terminal source and drop it in with a wire under the control voltage. Notice we're at about 150, 160 hertz right now. So at 5 volts, not much changes because they're the two 5K resistors. We get a little bit of a frequency shift. 5 volts is very close to 4.5, which is halfway from 9 to 0. So let's do a little bit more of an extreme change. So to 3 volts, we can see that we really sped up the frequency quite a bit. Now we can listen to the tone. Say, do a larger frequency like 6, and we're able to noticeably slow down our oscillator. Again, using just the external control without having to use any pots or changing out capacitors or resistors. So this provides a way that you can adjust the pitch of an oscillator from an external source. I'm back to looking at the audio frequency, and I've created an external power supply, which for a moment is just a potentiometer, one leg connected to 9 volts, the other leg connected to ground, and you can see in the lower left-hand corner of the screen I've got the voltmeter reading. I've put a small resistor in series with the potentiometer so that I can never turn the pot all the way down to 0 resistance and have a short circuit. You can see on the output of the pot, the 3rd pin, I am able to adjust the voltage down to 0 and all the way up to about 8.7 with the 9.3 volt battery. Alright, let's take that pot output, which is on a 2nd yellow cable, and plug it into control voltage. Hear the pitch change. And loose connections are going to make it wobble around. So it's often important to solder audio circuits. What a great range of frequencies I can get to by changing that voltage. I disconnect it, I lose my modulation, and I go back to a default pitch. So here's another more exciting final example of controlling frequency. In this case, I'm going to use a MIDI keyboard that goes to a CV or control voltage converter and actually bring that into the control voltage. So now I have an external piece of equipment which is controlling my 555 timer. Now it needs a little work, and this is going to be the subject of next quarter's course, Physics 231. Hope you can join me in Physics 231. Here's the experiment 17 assignment, a double-weighted assignment for those of you taking the class for credit. I'd like you to start by designing and building an astable 555 timer that flashes an LED at a frequency of 2 Hertz, so that's flashing twice per second. Describe in your logbook how you design your circuit, how you choose R1, R2, and C. Show me your calculations, and then upload a video of it functioning. Keep in mind you have to modify the audio circuit, which is the only one that's shown for the simple astable circuit in the textbook, in order to have it flash an LED rather than power a speaker. You may not need the capacitive coupling, for instance. Then instead of using a MIDI keyboard or a potentiometer to control the circuit pitch, let's use 2 555 timers in a stable mode, the first to modulate the second. So we're going to modulate the pitch rather than the amplitude, using 2 555 timers to make a warbling siren sound. That will be our final experiment with the 555 timer. Please explore some of the modifications that the author suggests in the circuit and demonstrate those in your video.